Good afternoon, it's me again, Jean-Louis Van Bella. I'm an amateur physicist. Today I want to talk a little bit about the difference between low energy and high energy physics. I'm gonna mainly, present something that you don't see in textbooks. It's a bit of my own appraisal. Low energy physics, I would say, are based on I would say scattering experiments, where basically what I show here is, you have a beam of incoming particles, and you're gonna send that towards a target, which has some scattering center. The target is here, and that target may be, a whole bunch of material, crystal lattice. That was surely the case in the early years, when Thomson discovered the electron, and when Rutherford sort of discovered the nature of nuclei and their size by gold foils and sending alpha particles into it. So that's all low energy, and the assumption there is that we have a pretty massive target. We send A's in, particle A's in, and I put an X prime here because the target may be acquiring some kinetic energy or lose an electron if we're talking about atoms. So the target is not something that is it's heavy, but it may change a little bit by the impact of the current. But it is low energy, and the comparison between the energy of the incoming particles and this massive target is huge. So that's low energy physics. And then you will have outcoming particles, which if it's photons, Compton scattering, then these B particles will be like the A particles, but like in Compton scattering, they will leave some energy that gets absorbed by the electrons with which they interact. So that's sort of the reaction, I would say, and I'm going to talk about the thing is, of course, with these experiments, you want to know more about the structure of your target. And I'm going to talk about that, about Thomson and Compton scattering in particular, because low energy physics is basically, quantum electrodynamics. It's about electrons, about photons, and how they interact. And yeah, I'm going to go a bit into the methodology of that. Now, high energy physics, I'm not going to talk too much about that. But it's about high energy physics is, you're going to have like particles smashing into each other, or in a linear accelerator, have equally massive particles being accelerated and smashing into a target that is very, very much like the incoming particles. And so there we talk about, I think, the most interesting or mysterious thing still is, matter, antimatter, annihilation creation, or as I call it, pair annihilation and creation. So the first ones in the 60s were basically electrons and positrons. Let them crash into each other and see what comes out of it. And then the question is, do charges really, opposite charges really annihilate each other? Do they disappear? And I'm going to talk about that in a moment. The interesting thing is, I think in the last 2 years is, I have a pretty classical view of quantum mechanics, and I'm happy to see that the archives of the early Solvay conferences, those ones before the Second World War, got recognized as UNESCO World Heritage. That's interesting. It means also they're complete, they're accessible, and that's probably my retirement project to dig into them and see where, in my not so humble view, quantum physics went went a bit wrong off the track with all kind of weird theories, inventing new contact forces or virtual particles ferrying energy, momentum around, etc. The other interesting thing is, I think, in the last 2 years, is that I always said I criticized, the nature of modern day experiments, in the sense that there's little competition, and it's close to impossible to do these high energy experiments, because they require these enormous machines. And basically, you have Stanford's linear acceleration, you have CERN, a 22-kilometer ring, which was first used for electron-positron collisions, and later for hadron, the Large Hadron Collider, charged particles, matter particles. And so what you see happening is that finally, I think, and that's good, is that the data is being released into the public domain. So CERN is really actively looking for a much larger mass of maybe people like me or other researchers, to give them access and come up with what I hope will be some kind of alternative standard model, or a more realistic model, I think, that does not invent things you can't measure, like gluons and quarks and all these things, mathematical factors that are being ontologized, and you have to take it for granted. I think that's all going to change. I don't know if this release of data into the public domain is triggered by these huge Chinese effort to build the same kind of machines, but on a much larger scale. China is going to build, instead of a 22-kilometer ring for particle collision, a 100-kilometer ring, and that's going to allow them to tap into much higher energy levels and hopefully discover new things, although I privately hope they're going to rediscover the old explanations. So let me go back to my presentation. Go to the start. The low energy physics. It's sort of well, let me first go to my model, actually. And my model is you will need some math. This is a Wikipedia GIF, an animated file, where you can see sort of what my electron model and probably also proton model is. The cosine and the sine, you can interpret them basically as a bivector combination, with the sine being perpendicular to the cosine. That's basic elementary math. But if you look at it dynamically, with a phase that changes, we're talking about an oscillation. Oscillation has a changing phase, which oscillates between 0 and 2 times pi. Then you can imagine that such oscillation is actually it's an orbital oscillation, but that it's the result of two linear oscillations, perpendicular one to another. And that's basically the model, and it's not a new model. Let me put it, let me summarize it here before I dig into these cross sections and how you might confirm this model. This is basically it, where we have a frozen picture of this oscillation, and we can the wave function basically can be written as a this complex exponential, where we have the phase, and it doesn't need to be the unit radius. One, well, we can multiply it by r, some other radius, or by a. And then we have a times a cosine, a times a sine, and then the imaginary unit, which acts as a rotation operator. So I said we have two oscillations, a vertical one, horizontal one, and let me clean up my sheet. And from there I have sort of an intuitive interpretation, I would say, of the Planck's-Einstein's mass-energy equivalence relation. not sort of, you get this thing out of special relativity theory and also out of electromagnetic theory that basically shows that the velocity of light um, is a constant, and it's the limit to whatever velocity of a signal, of a particle, of a photon, of everything. It's the absolute limit of speed in the universe. And the interesting thing is you can combine it then with what I do is sort of derive a bit or interpret that mass energy equivalence relationship in the context of the quantization of nature that Einstein and complemented by Planck discovered, both for light-like particles, photons, and then de Broglie had this genius to say, well, matter particles should also have a frequency, and the mistake he did is that he thought of it as being like photon-like, some linear oscillation. I'm saying like no, it's charge. What is Dirac talked about the equations of motion. Motion of what? Well, for matter particles, it's charge in motion. And if you think about this orbital velocity, and you think of charge, a naked charge without any other properties except its charge, plus so much Coulomb, minus so much Coulomb, and the unit charge, it's an absolute constant in nature, plus one or minus one. And we think of that naked charge, going around and around in this oscillation, and I'll explain how in a moment, what keeps it spinning. Then you can write it as the radius times this orbital frequency. So in the case of matter particles, I argue that Planck-Einstein relationship should be interpreted as an orbital rather than linear frequency. And then if we have these three equations, we know the energy is, of course, the energy. And there's a kinetic part to it and a potential part to it. I'll explain that. The electromagnetic field, here, that we have a ring current. And so that keeps it spinning. I will go to that in a moment. But if we combine these three equations, the energy is the energy. So we have mc squared, we replace a squared then. And then we have this radius of the oscillation, which is equal to h bar times the frequency. And in the denominator, we have the mass. Mass is a factor of proportionality. If we have a linear oscillator, you know that classically the energy in the oscillator will be proportional to the square of the radius of that oscillation, or the amplitude of that oscillation, and the frequency of the oscillation. And classically, it will be the factor of proportionality will be the mass factor on a classical spring, right, with a mass will be that mass divided by 2. Okay, so if we have 2 of these oscillations, and it goes round and round, as a result, we should have 2 times, so the factor of proportionality is, so we have the energy is in this quantum mechanical oscillator, I would say, is the mass times the square of the amplitude times the square of the frequency. So what is then, because that's what we want to know, what is the amplitude of that oscillation, what is the radius, what is the radius of the electron, basically, because that's what we're talking about, point-like charge. And that was the mistake that Dirac and Schrödinger did. I think they did not distinguish between the electron and the point-like charge inside of the electron. They thought of what all mainstream physicists are still thinking, that elementary particles are point-like, have no structure, while all the experiments, of course, show that they do have a structure. But yeah, you see here a square is this, and in the end you find the Compton scattering radius. What is Compton scattering? Well, there's a photon coming, right? Photon really is actually point-like. It's an oscillating field, an electric field vector that goes up and down, and then bivector and magnetic field. But really at any point in time, it is only at one point. And of course, these vectors, bivector, go up and down, and that gives it a linear character over one cycle. Sorry, one cycle is like this. It will pack 1 unit of Planck's quantum of action. But it is point-like, and so, when it hits an electron, there are 2 possibilities. Either, let me know, maybe, do I have a figure? No. Oh yeah, I have it in, probably here. Yeah, just to say historically, actually, this idea that I'm presenting now is not new at all. Huh? Where we would have, you know, a naked charge tittering around, as they say in German, moving around. And Erwin Schrödinger advanced that idea, but his contemporaries did not pick it up. Dirac and even Einstein. But Paul Dirac mentions this idea quite prominently in his Nobel Prize lecture. He said the variables a wave equation his own, give rise to some rather unexpected phenomena concerning the motion of the electron. It comes out of Schrödinger's equation and Dirac's equation. This elementary wave function is a trivial solution to both wave equations. And he says basically how we must interpret this is that an electron, which seems to be moving slowly, because it has well, not a huge mass, but at least 0.511 mega electron volt divided by square, so it's heavy. But there must be a very high frequency oscillatory motion of very small amplitude superposed on the regular motion which appear to us. And so, and he says is there the velocity of the electron, that's where he confuses the electron with this point-like charge in time, equals the velocity of light. That's what we say. That was said in 1933. We can imagine a point-like charge, a naked charge with no other properties, no rest mass except its charge, and that is going to sit around. It's not going to sit still. It needs to move around, and the way it's going to move around is dictated by that Planck-Einstein relation. So he immediately notes that the prediction, which cannot be verified directly by experiments, because the frequency of the oscillatory motion is so high and its amplitude is small. But, and that's the experimental validation for me, other consequences of the theory are inseparably bound up with this one, such as the law of scattering of light by an electron. And that's what I talk about here. What I talked about here, when you have indeed a photon, it may mess with the electromagnetic field, because that's something I need to show. I hope I have it somewhere. Yeah, here. If we imagine indeed sort of, what you see here, a ring current. Of course, it's not a continuous. It's really a point-like charge, going around at the speed of light. And the remarkable thing is that, according to classical electromagnetic theory, that is going to create a magnetic field, which is gonna, in our case, keep that point-like charge in motion. So half of the energy is the kinetic energy of that point-like charge. It's half the electron mass, and the other mass is the equivalent mass of the energy in the electromagnetic field. So we have something special, because you will say, oh, this is like what the slightest disturbance should make this electron collapse, and that's that's the mystery, and not the mystery I'm saying is when there is a disequilibrium situation, then a photon messes with the electromagnetic field or directly hits that charge and scatters back elastically. How should we imagine that? Well, when the photon hits the charge, the field has a charge to act upon, and so that charge is going to get out of its equilibrium situation, is going to go up and down. And so it's immediately going to radiate that energy away again, but it's going to do so in a way that respects the Planck-Einstein relation. So it's going to radiate another photon away, and as we know, a photon has a definite angular momentum, which is defined by its frequency, its wavelength, and that's going to be exactly the same as the incoming photon in the case of Compton scattering, because it's elastic and no energy is being transferred to the electron as a whole. And so that's how I explain it. You will say, okay, what's the experimental evidence for that? I think there's plenty. In QED, you have what's called a coupling constant. and that's equal to the fine structure constant. And that fine structure constant comes up in many situations. There's an anomaly in the magnetic moment, and that's because this charge here is not exactly point-like. It's not infinitesimally small. It's very small, but not that small, actually. Its size is given by, the Compton radius. Here, Compton radius times the fine structure constant, which, as you know, is 0.007 something, almost 10%. So yeah, that point-like charge has a definite size, a finite dimension, not infinitesimally small, and that's why I'm going to talk then when I talk about high energy physics, why I don't believe it sort of just disappears. Things that have a certain size don't disappear. Okay. I have a lot to cover, so but yeah, so we have alpha, and in quantum electrodynamics, that's a coupling constant. And if you read theories, popular or not so popular, Feynman's QED, the wonderful theory of light, or you go on Wikipedia and whatever, you will find that indeed that alpha is a probability amplitude for an electron and a photon to couple, to interact. And it is an amplitude, and we know an amplitude is the square root of a probability. So the probability that's when you think physically, an amplitude is quite abstract. You can work with it, combine it with other wave functions. There's a whole, but basically a probability, you would want it to be based on like physical surface areas, because the photon has no surface area. Well, the only thing that we can see is like for Compton scattering, what is the chance of the photon hitting the point-like charge, or more generally, just interacting with the magnetic, electromagnetic, or the magnetic field that keeps that charge spinning. And the answer is there very clearly. Well, we have two radii. We have the classical electron radius, and we know that the surface or interaction surface would be PR squared, the formula for the surface of a circle, and we would divide it by p times the square of the whole thing, the whole electron, and then you arrive at the fine structure constant squared. So that makes sense, and that's what I highlighted, where and that's the interpretation of what Dirac said. This Zitterbewegung hypothesis makes a lot of sense because it is consistent with the scattering of photons by electrons. Just for the fine structure constant, I get a lot of a lot, 3 or 4 people over the last month who said, well, the fine structure constant, how we interpret it in terms of the von Klitzig constant, or this or that mathematical ratio. There's a variety of interpretations of the fine structure constant, but all of them are basically can be brought back to ratios between radii or surface areas. For pro memory, say the Bohr radius of an electron. An electron, as it appears mostly to us, especially in low energy physics, is going to be in some in atomic or molecular orbital. That Bohr radius is going to be 1 divided by alpha times the fundamental electron radius, the Compton radius. Compton radius, by the way, if you Google it, a word I coined because everybody talks about the Compton wavelength. And I said, if you talk about an orbital oscillation, then you need to do, you're not talking wavelengths, but the reduced wavelength or radius. But so that's 1 over alpha times h bar divided by mc. We can write it in terms, alpha, if we substitute alpha by the formula for it, and we have the mc, and it's also a nice formula, h bar squared divided by the mass of the electron times the squared classical electron charge. It's a sort of normalized a symbol that just substitutes for 4p times the electric constant divided by the square of the electron charge measured in Coulomb. So it's a nice formula, an obvious one, an evident one, and that's another. If you ask me how many times can you rewrite alpha, the fine structure constant, well, many times. I found at least six, seven ways to rewrite it. One of them I like here is indeed sort of, we can write it as a square root of the ratio of these two. And we can also, of course, write it as the ratio, not a square root of, but the plane ratio of the classical electron radius and the Thomson radius and the Compton radius. So there's so many ways to rewrite this, and once you start playing with these things, it makes sense. Now that's the evidence. Let me be critical of myself. I don't know why this thing is there. And go and show you basically here when you look at the Thomson at Codata, so they make they're sort of the authority on what comes out of experiments and values. The interesting thing is if you go to the Thomson radius, they don't use that word. They say, well, we have a Thomson cross section that comes out of experiments. They give both a formula for it, a very precise one, and a numerical value with a standard uncertainty that is of the same about of the fine structure constant. But the interesting thing is this formula. I highlight I wrote them. They replace the classical electron radius or Thomson radius by alpha to the power 4 times the Compton radius. So that should be by the power 2. And then let me go back to my notes. Because now we're going to talk about what does it mean, this cross-section, and why is that a p divided by 3 factor there, because that's a large factor. Just to sort of note what I wrote, if you have that formula in the NIST formula, so we have the factor here, and then if we replace it by alpha times the Compton radius of an electron, then we should have an alpha square instead of an alpha 4, and you can work it out and go on Wikipedia and cross-check with textbooks. This is the formula you're going to find, and you can indeed replace that by alpha square times h bar divided by mc, not alpha to the power 4. I sent NIST a small note to ask them where they got that from, because I'm pretty sure it must be some mistake, but it's kind of weird. Yeah, I'm going to talk about these formulas. So this Thomson cross-section is, it's the formula I have here is sort of, it confirms my theory, basically, that we have, something like a classical or Thomson radius for scattering and interaction area, the square. We don't have the pi there. We do have the pi, but we have this factor. So we have this sort of makes sense, right? Pi times the square of the classical electron, but we have a factor of almost 2 here. 8.8 divided by 3, so that's a lot. And you could say, yeah, in terms of amplitudes, to take a square, it's not that much, etc. And Feynman would say, if you have a formula and you see these factors like 8 pi divided by 3 geometric factors that you have like in the formula for the volume of a sphere, which we know is the cube of the radius, and then we have a 4 pi divided by 3. So this is like a geometric factor. But of course, I'm not like Feynman who says, well, don't care too much about it. Your theory is going to be fine if that's the only problem with it. But I do worry about it, and I dug into it a little bit, and that's where hopefully this lecture will become somewhat more interesting and enlightening, because I'm going to talk about how is a cross-section being defined and measured in mathematical formula and in physical experiments. So how exactly? I could refer you to the Wikipedia article on scattering across sections, and it's a confusing article, I think, but it's also a good one, because they do distinguish between very various very different physical situations, where they talk about Coulomb scattering, or what I showed, you fire photons into an electron or alpha particles into gold lattice crystal structure. And so they distinguish these the various physical situations and say, like, well, for a scattering cross section, you do need some kind of model of how the material looks like and what the particles really are, and I like it. I like that. And then they conclude. They say basically, well, there's no really simple relationship between a scattering cross-section and the physical size of the particles. But there is a relationship, and they show that for the various physical situations. Now, as it turns out, I looked into the Thomson, differential cross-section, and I'm going to talk about the difference between a differential cross-section and, well, the real cross-section or total cross-section, and you need to integrate. You need to integrate this, and they give a formula for that, and I'm not going to go too much for that. We recognize this the surface area, the square of alpha times the Compton. The C stays for Compton radius, or the classical electron squared. Well, I said we don't have the pi here. And then there's this funny thing that oscillates. There's a factor there which varies with not with the phase. The symbol usually for the phase, but with the scattering angle. We see a photon going in, photon going out. I can clean up, yeah. And you're kind of going to have a certain scattering. So here we're talking about this naked charge, QE. We know it's the electron is a lot bigger, but we're talking about elastic scattering. Photon goes in, comes out, and messes with this charge, which is naked charge, and naked charge is out of its is in disequilibrium, and its motion is going to radiate the energy it absorbs straight back out. But straight back out, a photon is a photon and also needs to pack 1 unit of physical action. So that's h bar. But that's what happens. It doesn't pick up any other kinetic energy, and we assume that this naked charge is inside of an orbital electron. If it would be a free electron, then of course we could imagine that it would pick up some kinetic energy and change its motion in free space, as they call it. So we have a periodic function there, and this is then the funny thing, this differential cross section. I'm going to talk about it. Why we need it. This differential cross section depends on the scattering angle, but it does not depend on the energy of the incident photon. And that's with Compton scattering. I may give a reference here to Professor Dr. Leclerc from Alabama University. You can Google that, PH 253 Compton scattering. Very nice article on Compton scattering. But in Compton scattering, you don't have something like that. The energy of the incident photon does matter, or to be more correct, the ratio of the energy of the incident photon with the energy of the electron. So let me clean up my whiteboard. So yeah, we have a differential cross section here. You can already feel if you have sort of something like this, you're gonna probably want to integrate it over some kind of a surface. That's what I'm gonna do in a moment. Over that. What is this angle here? That's the thing I'm going to talk about now. Yeah, that's sort of historically. I like physically, but what is this? Yeah, what is a differential cross section? Let me first start with what you would do and think of when you think about a cross section as a surface of interaction. Again, we have this reaction here. An incoming particle hits a heavy target, and then these heavy targets get modified somewhere, gets a bit of extra, and we have outgoing particles. You would think that, well, this is actually where things start become a little bit weird, is that the cross section, the very first mathematical definition of it is actually more one in terms of probabilities or basically, let me write it down here. We have B particles coming out and A particles coming in, and so there's going to be a certain rate of B particles that arrive at the detector, and then we have a current, so many incoming particles, A per square meter per unit area, and also per second, right? And so these two rates give you a ratio, which is a probability. It's a number between 0 and 1, and it has no physical dimension. We can modify this one. Our target area, the X, may consist of many targets with a lot of empty space in between, and then n is, for instance, going to be the number of nuclei or the number of electrons in the material in which we fire our. So you see, the cross section actually is. And that's what I want to know. Mathematically, physicists often think not in terms of surface areas, and of course they're going to use these numbers to determine the structure of the material, but they think of something very mathematical, a probability ratio. So that's the definition you need to start from. And we're talking about at the detector. The problem is you will have many detectors, and there will be a lot of space between them because the area in which they detect stuff is surrounded by other things, and so the detector or the detectors will usually occupy a very small space only, and only pick up B particles at very specific points in space, and the other B particles will go undetected. So that's then where and that's a bit of rocket science, I think, now. The idea is, we need to normalize and think in terms of unit values. That's the idea where of a solid angle comes in. It's like the three-dimensional equivalent of a radian. Yeah? And we know a radian on a circle goes from 0 to 0 is 2 pi. And so that's sort of a normalized thing on the unit circle. I found the term definition of this solid angle as a square radian, and the three-dimensional equivalent of the radian. Not very appropriate, because we're not talking about a unit sphere, we're talking about a big sphere, and the best definition I found is that sort of the solid angle is a measure of the field of view. Suppose this is your eye and you're looking at the moon, the distance to the moon and the surface area, or the physical size of the moon, is going to determine your field of view. So it's a measure of the field of view that a given object, it could be the moon or the sun, covers. In our case, it's the field of view that a detector covers, as seen from the point of interaction, the point of scattering. So you should think of A here, in our case, as being the detector, or the surface of the detector, at least. And just for the record, I will let you Google that. The radian goes from 0 to 2 pi. One steradian. So 1 unit of solid angle is defined as the field of view covered by that if. This is the definition of the solid angle is the surface area divided by r square. Now, if A would happen to be A is r square, then we have 1 steradian. Of course, you can readily see that we change r, or we will probably have the same ratio. But if we take a larger surface cap, or I would say as the in that sphere, then we have more. And I'm not going to go into mathematics, but instead of going from 0 to 4 pi to 2 pi, a steradian goes from 0 to 4 pi. So with 4 pi you cover basically the whole sphere. Your field of view is the whole sphere. And that's sort of where I'm gonna go more in detail. But if you look at the diagrams, I'm taking here a very good one of Matthews and Walker, where you will indeed see that cross sections. When you look at the units, they will involve the unit, an area unit, centimeter square, a small one maybe, and then 1 unit of a steradian. Instead of 1 radian, 1 steradian. And that's what I said here, in real scattering experiment, you will have like your scattering angle will be from 0, 8, and you will have a detector only at, let's say, 30, 60, 90, 120 degrees, 180, 150 degrees. And there you will do your measurements, and you will find, a rate of particles coming into your detector, and you will normalize, standardize that, and you will find some geographical shape, and then you will map for instance, through a least square method. You will fit a curve to that. That's how things work. Now, what I'm going to show is that this is the model basically. This does not apply to my model. This is the formula that is being used to calculate the Thomson cross section. But I said here, it starts with this thing here. As this target, I said it's a free electron or an electron in an atomic or molecular orbital. It is not like sending alpha particles into material where you have Coulomb interactions and other stuff. No, an electron photon interaction is fundamentally different. But so they apply the same formula to calculate the Thomson cross-section, and that's where I think this factor 8 pi divided by 3 comes up. But to go on, so this would be the situation where basically, we have a detector here, and we have a detector here, and maybe we have a detector there, and all these detectors are going to have a certain scattering angle. And then for each of these detectors, they will be at a certain distance away. Often detectors will, of course, be more arranged like that on a line. So then we will have an R that differs, right? And so that big sigma, capital sigma, again is not a scattering angle. It is really plainly that, in function of R, the distance that the detector is away. And I said if they're all arranged on some wall, R will be much larger for this detector, and but the surface area will be the same. So your solid angle, your field of view will change. And that's the thing where, depending on the detector, your measurement points, you will be very interested in the difference, of course, between the rate of incoming particles. But you to make sense of the data, you must be interested in the differential of that sigma. And that said, that depends on R, but not on A. The detector size is the detector size. And so R, on what's going to depend that? Well, if we have a detector here, we will want to write things in spherical coordinates, and we will have an azimuthal angle and a scattering angle, which develops as the polar angle. So then, as I said, the cross section, we can have this simplistic definition here, right? But the thing is, when you have many detectors and points and whatever, as I said, you will want to see how your cross section, as measured in terms of thing, how when I change, that big sigma, how my cross section changes. And for that, the change in the solid angle, there's an easy formula for that in terms of the polar and azimuthal angle. But this thing, the difference from one detector, what you capture there, to a detector at a different position at a different distance, that depends, of course, on the experiment. And this is the funny thing, that in this cross section they give a precise formula. But at the same time, what should happen is that if you have this ratio, which is very interesting, and you have points, then you will want to integrate after fitting your curve, and you will take an integral, as I write here, a surface integral over from 0 to 4 pi over the full length of the thing around, and integrate that ratio over that infinitesimal small differences. Well, if you have fitted the curve of the solid angle. Okay, I don't think I did a good job at explaining that, but if I go very slowly, then you surely won't listen and you will have lost me. But that's sort of where these things, how these things work, how how cross sections are measured, and where I go back to that comment from Wikipedia. There's no simple relationship between the scattering cross section that is calculated in this case for Thomson scattering and really the physical size of the particles, especially not because, as you can see, the situation here and the formula they use for calculating cross section is based on a physical situation like this one, and it doesn't resemble, not at all, that situation where we think of an electron as a charge in motion. So that's where I feel validated, and also criticism like, well, you didn't, your formulas don't agree with experimental data. Well, I said cross sections are something different than these formulas that I show here, and they're also very different than what comes out of very solid quantum mechanical experiments, this coupling constant, where the fine structure pops up and matches my idea of a naked charge that is not infinitesimally small, which has a certain spatial dimension, but no rest mass. It is a funny idea, and that's where now we're going to go to the thing that intrigues me most, and where I want to really, where I'm happy that CERN releases a lot of data. Per annihilation and creation. So in low energy physics, I said the worldview is really very much this dichotomy between charges and fields. When we have a field, that field becomes a force. A field is going to expend itself on a charge, but it's it's a bit like kinetic and potential energy. A pair of concepts. So I don't think in terms of bosons and fermions. No, I think there are charges and there are fields, and charges do give rise to what I call matter particles, which have a rest mass, and fields who are like a force without a charge to act upon. It's only when it meets a charge that it sort of is gonna traveling field like a photon is gonna stop in its tracks, so to speak, and gonna give that charge some kind of new motion, which is a non-equilibrium motion, and that's how things go. But what happens when an electron and a positron come together? So I tried to think about that, and I said in my worldview, an electron is, this thing, a negative charge, point-like charge, the Compton or classical or Lorentz electron going around and around, and a positron is the same except that the charge is positive. And so they're going to attract each other because of the Coulomb attraction. They, I also think, like, before they, if they don't want to, we'll have to come close together. I said in this worldview we have a magnetic field that is generated by the ring current. But the magnetic field is opposite because we have a negative and a positive charge. So if they come very close together, the magnetic fields need to line up. Otherwise, the magnetic force, and we know in relativity, it depends a bit on your frame of reference if the force is electrostatic or magnetic, but they're going to repel each other enormously if they come to very close distance. So I think that if we want to have a sort of physical interpretation, is that the magnetic moment of the two of the electron and positron that meet each other needs to be opposite. Their spin, and will be 1 unit of Planck's with just quantum of action. But so the magnetic moments must be opposite for an electron and positron to come together and then annihilate. So you have these questions then, how does the superposition principle for fields actually work? When these come together, it's clear that the only components that will matter, I said when it goes out around, these won't matter, and you will have magnetic field vectors that are opposite and equal in magnitude. So according to the superposition principle, the magnetic force should like disappear, but we know energy doesn't disappear. So how does the energy conservation principle actually work? I will meet that. I have no answer to that, but it makes me feel like experimentally in the classical view, and I'm going to talk about that. When they annihilate, we have like two gamma ray photons, and they carry all of the energy, the kinetic energy and the potential energy, so the field energy and the energy that is in the kinetic energy of the or the relativistic mass of the naked charge. They're going to carry all of that energy. So the energy conservation principle in a mainstream or not so mainstream view, I will talk about that. There is energy conservation. So no, there's no way that these fields evaporate. So superposition principle seems to be a mathematical principle here that does not apply in this physical situation. The main question for me is where does the charges, where do the charges go? The in the literature mainstream, and I'm actually not so sure if it's mainstream because I'm going to show you. It's like yeah, the charges disappear. Charge conservation holds because we had a plus and a minus together, they're zero. But it's not local charge conservation, and I think the greatest physicists of all time, including Feynman and others, said charge conservation is something holy, and it underpins actually quantum electrodynamics. So at the same time, when we're thinking about what is called this Dirac process, where a pair of charges just sort of evaporates into photons and the charge disappear. First, that pure Dirac process, I think I have not done too much research, but when you look at these experiments of electron-proton colliders, like the Large Electron-Proton Collider of CERN, let me show this paper here. The LEP collider, the Large Electron Proton from design to approval and commissioning. That's an old paper I found. And the interesting thing about the paper is that they say, we are building this 22-kilometer ring in an enormous luminosity and very high beam energies and etc. Not to find the, let me make that bigger. Not to find these two gamma rays, but really, find this Z boson or W plus boson or W minus boson. So they're not looking for high energy photons coming out of an electron positron position, but for these bosons that were predicted. Now I won't look into this more because you will say that's that's interesting first, because these WZ bosons are usually we talk about them in the context of very different collisions, proton antiproton collisions, or other hadrons, as they call them. I think it's a bit of an artificial term. But yeah, this is something intriguing when you look at the history of CERN's Left Collider, is that the team was actually not looking for this hypothetical and theoretical Dirac process of annihilation, which in the view, I think, me myself, was like the classical example of matter gets converted into energy. I said there's a mass energy equivalent, but it doesn't mean that charge somehow magically becomes field energy. So the thing is, with the LEP collider, they found them. The intriguing thing is still a bit that they, based on these experiments, they say, well, they have a definite mass with some uncertainty, but about 80 giga electron volt divided by c squared, the equivalent mass of the energy of a W plus minus boson. And I should look it up for a Z boson. According to me, this matches the energies that are in the beams. So if you would do experiments with very different beam energies, we might find other bosons, I would say, that carry charge. So I do think in this electron positron annihilation, we do not have two gamma rays, or four, it depends a bit on when you look at it. We do not have a Dirac process, but we do find these, they're not virtual photons, they're not real photons, they carry charge. So I don't think you can pile them on top of each other because they have a definite size. So even the term bosons for these W plus minuses and the Zs is not a good term, I think. But that's where we are, where I can imagine in these high energy collisions, we do find disequilibrium states marked by real, very short-lived particles which carry enormous energy and charge. In the case of the Z0 boson, positive and negative charge, that's like the neutron theory, or negative and positive charge combined. And so the neutron is neutral as a whole, but it can, eject a negative or a positive charge in these nuclear reactions. But that's my theory, and it's not mainstream, and but I said I'm happy to see this, that a lot of data is finally in the open field. It should have happened a lot earlier, where lots of data is being released and we can see what actually happens, and instead of a very select team of researchers, which of course to keep on going and convince politicians to invest more and more in these machines or upgrade them. They must have a research agenda. So that seems to be one of always looking for more and more exotic particles to fill a theoretical gap by opening new theoretical gaps. Sorry to be cynical about that. So that's it. I'm gonna quickly see on my notes if I want to add something. No, I had some other slides, but they're not so interesting. Let me see how long I talked. Almost an hour, so that's good enough. Thank you very much. I will upload this, and then tomorrow I'm getting a new bike, and I will be on the bicycle during this holiday. I'm on holiday actually in July, so that's why I have time for these things. I wish you a very nice day, and I hope you enjoyed it. If you did, please like it, and go read my papers. Show it here on ResearchGate. I'm quite open on these models. I calculate forces inside and stuff, and please double check, because that's maybe something I want to add. You will say like, wow, how can an electron be so solid? If you calculate the forces, the electromagnetic force of this tiny little ring magnet, you arrive at 0.106 Newton for productive mole. That's enormous. That's a force that gives a mass of about 106 grams, an acceleration of 1 meter per second. So, and we have it on a very tiny scale, and so it's not a miracle that an electron is difficult to break. I would say you can only break it by sending in a positron with huge energy, smash them into each other, and then you get something new. You're in a field of high energy, but in low energy situations, that electron is not the unstable thing that it looks like when you see my theoretical model. No, the forces inside are huge, and I said the fine-tuning problem, as we call it. Why is the Planck-Einstein relationship so exact? Or why is the mass-energy equivalent relation so exact? Well, that's how nature is. Call it statistical determinism. But it's determinism, because I said we can't really observe directly, the motion of the naked charge inside. But for me, it looks quite normal. There's no big mystery in it, even if I call this paper one of my mystery papers, Mystery 104, on zeta-beweging models and magnetic anomaly. So have fun with that, and I wish you a very nice day again.